Okay, before I move on to these examples, let me tell you there is some reading material that you could look up about the error term, which will let you know how close you can get to the exact answer, but I'm not going to cover the error term in these lectures. So I'm just going to go ahead and just cover the two rules. So anyway, the square root of 1 plus x to the fourth dx, that's an integral that can't be integrated using algebraic techniques. So what I'm going to do is I'm going to see if we can do this using the trapezoid rule with n equal 4. So first of all, since n equals 4 and a is 0 and b is 1, then if you do 1 minus 0 over 4, then you'll see that delta x is 0.25. So if we start at 0 and then go 0.25 until we get to 1, the next point would be x1 equal 0.25, x2 equal 0.5, x3 equal 0.75, and then finally x4 equals 1. Now remember, this is the trapezoid rule formula. So if I do b minus a over 2n, that would be 1 minus 0 over 2 times 4, so that would be 1/8. So that would give me 1/8. And then I would need to find out, I would need to, in this bracket here, I would need to sum f of 0 plus 2 times f of 0.25 plus 2 times f of 0.5 plus 2 times f of 0.75 and then plus f of 1. Now all you do is just plug these into this function here, the square root of 1 plus x to the fourth. And so that would be 1/8 times the square root of 1 plus 2 times the square root of 1 plus 0.25 to the fourth plus 2 times the square root of 1 plus 0.5 to the fourth plus 2 times the square root of 1 plus 0.75 to the fourth, and then plus square root of 2. Now if you want to go ahead and figure out what these square roots are beforehand and then plug them in, that's fine too. But I just went ahead and just gave you the expressions like this. Now when I added all of this up, I got like 8.774364, and then you multiply it by 1/8 and you get 1.096975, and that's accurate to 6 decimal places. Now if we do the same problem with Simpson's rule with n equal 4, then basically we still have n equal 4, a is 0, b is 1. The x values are still the same, 0, 0.25, 0.5, 0.75, and 1. And the difference here is I would actually have b minus a over 3n, so that would be 1 minus 0 over 3 times 4, which would be 1/12. And then I would do f of 0, and I didn't write this down, but that would be square root of 1. And then I would do 4, remember these alternate from 4 to 2. So I'd have 4 times f of 0.25, so you'd plug 0.25 into that function. And then you would have plus 2 times f of 0.5, so you plug 0.5 into the function. And then plus 4 times f of 0.75. And then finally the last term would be f of 1. And when I added all of these up, I got 13.072961. And then when I multiplied it by a 12th, that gave me 1.089413, and when I checked this on the Wolfram Alpha site, the answer to 5 decimals was 1.08943. So I've got 1.0894, so I've got it accurate to 4 decimal places. So that's not too bad, okay? Not too bad. Now here I'm just doing the same thing with different functions. So this time I've got sine of x squared, which is another non-elementary function, and I'm integrating from 0 to pi. So on that one I still have n equal 4, a goes from 0 to pi. So I've actually got these wrong here. Actually I didn't mean to go 0 to pi, I think. Actually, I'm wrong here. I actually have it wrong up here. This should be 0 to 1, not 0 to pi. So make that a 1. Okay, so again, n equals 4, a is 0, b is 1. And so I'm going to get the same values for x0, x1, x2, x3, and x4. And so b minus a, for the trapezoid rule, b minus a over 2n would be 1/8 again. And then you do f of 0, and then plus 2 times f of 0.25, then plus 2 times f of 0.5, plus 2 times f of 0.75, and then f of 1. So basically what you would have is you'd be calculating the sine of 0 squared plus 2 times the sine of 0.25 squared, and plus 2 times the sine of 0.5 squared, plus 2 times the sine of 0.75 squared, and then plus sine of 1 squared. Now make sure your calculator's in radians when you calculate that. So when I added all of these up and then multiplied it by 1/8, I got 0.421159, and that was with the trapezoid rule. All right, let's see what happens when I do the Simpson's rule. So with Simpson's rule, I'm still using n equal 4, a is 0, b is 1, and so x0 through x4 is going to be the same values. But in Simpson's rule, I'm going to have b minus a over 3n, so that's going to be 1/12. And then I'm going to do f of 0 plus 4 times f of 0.25, and then alternate to 2 times f of 0.5, then back to 4 times f of 0.75, and then plus f of 1. So that's going to be sine of 0 squared plus 4 times sine of 0.25 squared plus 2 times sine of 0.5 squared plus 4 times sine of 0.75 squared plus sine of 1 squared. And then when I added these up and then multiplied by a 12th, I got roughly 0.31, 0.309944. Now, Wolfram alpha actually says the answer for that is 0.310268. So I'm not as accurate as I was on the previous example with Simpson's rule, but if I wanted to be more accurate, I could make this be 8. Now it would take longer for me to do the math, but I would get a more accurate value. And then again, like I said at the beginning of this lecture, there is information here on how to determine the error. So I won't, and again, I'm not going to cover this here, but there are ways to determine your maximum error based on the value of n that you use. Okay, so that's pretty much it. That's all I'm going to talk about on the numerical integration. But you can see that there are ways to evaluate these non-elementary integrals over a particular interval.